Good evening, everyone. Can you hear me?
Audible, sir. Yeah. Sir, you are audible.
Good evening, everyone. I am Jessica Sarani, Program Coordinator of Building Services Industrial Campus. It's a great pleasure to welcome you all to the final session of our program on Central Chilled Water Plant Design and Efficiency Optimization. Over the past several days, we have had a very comprehensive learning journey. We begin with the fundamentals of central chilled water systems, understanding their components, configuration, and application. We then explore system operation and control, focusing on how energy performance is influenced by different system arrangements and structures. Moving forward, we dive into advanced control strategies, including variable flow systems, chiller frequency, and optimization techniques aimed at improving overall plant efficiency. Finally, we looked at the practical aspects of design and implementations, including field devices selection, commissioning, and real-world case studies. Today's session is designed to bring all those concepts together. The objective of this panel discussion is to discuss practical challenges faced in reactor projects, share industry experiences, lessons learned, and best practices. Explore how modern technologies, automations, and smart controls can further enhance efficiency. Now, I'm privileged to introduce our distinguished panelist, Engineer Prasanna Narangoda, a highly respected professional in HVAC and sustainable engineering with strong involvement in ASHRAE and green building. Engineer Kolika Varnasi, an experienced building services engineer with extensive knowledge in chilled water systems, project execution, and system operations. Engineer Jagat Vikramasekar, a specialist in building automation, ERV systems, and smart technologies with a focus on integrating IoT and digital solutions. We are pleased to have Engineer Lakman Isru, CEO, Building Services Industrial Campus, our moderator, who will guide this discussion and ensure a productive and engaging session. With that, I encourage all participants to actively engage, ask questions, and make the most of this final session. Thank you all, and let us begin the discussion. Over to you, Engineer Lakman Isru, moderator of the session.
Thank you, Tasani, for your descriptive welcome address. So, as a moderator, so we have today our distinguished panel members. So, I will raise the questions to keep the continuation of this session. And also the audience, those who are joining with the Zoom, they are the CPD course participants who you can raise the questions as well from the distinguished panel members while the session is going on. Yes, so once again, from my end, I warmly welcome you, the three panel members, three expertise for the industry. No need to explanation further, and also welcome for this our audience, and also those who are joining in the YouTube and the Facebook. So you can share this link all over the world, and you can listening to this very productive panel discussion, and let listening to the our expertise expression for this field. Okay, without taking much time, I will take the questions starting from Engineer Kolita. So he's the one who start the session for the air conditioning system. Actually, just I want to explain you our team for those who are joining with the YouTube and the Facebook. This is the advanced air conditioning course which we did for our building service professionals, especially for focusing for the plant room design and its efficiency. So Engineer Kolita has covered all the fundamental system for the understanding the how this plant room has arranged. So Engineer Kolita, actually in your total discussions, so you brief about the components of the central chilled water systems and what are their arrangement like this. So in your experience, I think you have more than 20 years experience in these fields, I know. So in your experience, which system is typically has greatest impact for this especially for we are considering about not for the design but for the efficiency, but together with, so which will the greatest impact for the overall efficiency?
Good evening all. Thank you, Engineer Isuru. I mean, we actually consider, when we consider the chilled water systems, especially, I mean, we have two systems like water cool and air cool systems. So most of the time, if we consider about the water cool system, I mean, the component wise, there are like chillers. Major part component is the chiller. Then pumps, then cooling towers if water cool. Then like valves, piping network, then air separators, chemical treatment system, that chemical dosing system. Most, I mean, these components are in the chilled water system. But out of those, when I come back to your questions, I mean, your question was which component will contribute the most, I mean, energy consumption or the energy efficiency to the plant room. So out of those components, actually, chiller, even though it is water cool or air cool, the chiller is the component which contribute mostly to the plant room efficiency. So if I elaborate a little bit more, I mean, now if you take out of the plant room efficiency, I mean, nowadays we can even go like 0.6 kilowatt per ton. I mean, even less than that also, trying with controlling and sequencing. So I think Engineer Narangoda already touched those areas. However, out of the power consumption or the plant room efficiency, 80%, 70 to 80% of the consumption of energy will be taken by the chiller itself. So that is why the chiller will be the most critical item, playing the most the highest component in the plant room, consuming a lot of energy. So that is why we have to emphasize, or we are reiterating, or we need to be very much careful when selecting the chiller types and all those things. However, answering your question, it is the chiller that will affect mostly to the plant room efficiency.
Yeah, thank you, Kolita. I think you start a good startup that you mean about the chiller would be the major component for the plant room design, and for the efficiency wise, it is highly affected for the system. Yes, thank you, Kolita, for the good start for the session. Then my next focus is my question is then goes to Engineer Narangoda, who took this the middle part of this session. Actually, Engineer Narangoda, with his expertise, he covered about the control strategies and optimization. Engineer Naran, now you covered those areas. Now in Sri Lankan, I think Sri Lanka, we understood that the costs are rising for the many existing buildings because of we have not, but we install the good system, but we are not properly optimized. So what in your experience, what would be the gap, common gap you observe in the current chill water plant optimization when coming for the not optimize chiller operation? Actually, so we install both the chiller for the best efficiency, but we notice that there are some gaps. So what is your experience? You identify for the common gaps about this.
Thank you, Isru. Thank you for the question. Before that, there's a small slight adjustment of my introduction. I would prefer to be a MEP engineer than HVAC engineer. So slight change, please correct it. I'm a MEP engineer, not a HVAC engineer, HVAC consultant. Thank you. And also I would appreciate that you get my involvement for this course and also for this panel discussions also. Answering to your question, Isru, now, okay, Sri Lanka, according to my experience, since we are involved with many plant operations and plant optimizations, my experience that most of our plants are running on fixed set points. There's a first issue that I have noticed. We always encourage people to go on, operators to go on dynamic optimizations. That means basically dynamic chill water set point, dynamic condensed water set points, and static pressure resets, etc. But most of the plants, I'm sure, have seen that these three parameters, set points, are always constant, which is not getting any savings at all during partial load operations. And poor chiller sequencing is another issues. Not even sequencing not has been implemented most of the cases, but even it is there, it is poor controlling has been implemented, coupled with the chiller sequencing, which brings you finally staging functions, but not the efficiency is not maintained well. And poor chill water flow control also I have noticed in many cases. Though the VFD is there, it's just almost always running on a fixed frequency, or maybe a very minor variable margin, not getting the maximum the benefits of that answering to with respect to the pressure variations of the system and the flow variations and load variation of the systems. So that is one of the few of the issues that I have noticed, and there can be more. But these are the basic. What we have noticed is one of the very common phenomena is the plant is running on fixed set points, rather dynamic set points, and poor chill load flow control and poor sequencing. And also some systems are running purely manually. No even BMS, no even chiller plant manager systems coupled with them. This totally depends on manual operations. So you understand that having a manual operation or operator going there to the system, to the chiller, to the pump in 1 hour, 2 hour frequency period for a day will not be adequate to get you the required energy saving throughout the day. So operators going to the chiller maybe 6 times for a day, right? Adjusting its temperature or a valve position, etc. So we need a dynamic system, dynamic like software system coupled with that, like a BMS, chiller plant manager, with answering promptly to the building load variations, rather manual adjustments or manual overload. So those are the basic the issues that I have noticed. So thanks for the question.
Thank you, Narangoda. I think yes, you brought the good platform to my next invitees, the engineer Jagat, to bring discussion now, because you mentioned for the running at the we are not fixed speed running, so it means there's no controlling. Jagat, now this next question goes to you. Actually, you covered especially for the design, automation, and implementation. Now, while engineer Kolita is covering for the fundamental, and engineer Narang going to bring about these strategies. Now, you have covered this course about the design implementation for the automation plan. What do you think? How importance of these building automations and the data driven controlling to achieving this true efficiency, as engineer Narang mentioned, engineer Narang mentioned about what is the key consideration for in your experience, because I know you are you are very expert in this for the building automation system in the field.
Thank you, Engineer Isuru. Thanks for the opportunity. Good evening, everybody. That is a good question, and Engineer Narangoda gave wonderful opening for the answer even. Now, in his answer, he was emphasizing that the system should run on dynamic set point. Set point means the particular number that you want to achieve. If it's a temperature, we always define, okay, that's a 24-degree temperature. That's what user end needs. And when it's come to carbon dioxide controlling, we set it like 2000 ppm or 1000 ppm likewise. But those values will remain always as it is. These are the values that we want to maintain. But at the other end, the devices end, since the load is changing always, because outdoor temperature would change, the climate condition would change, number of people who are coming to the location, even long term, the building orientation, the certain office area, those things would change. So as he clearly said, we can't run the system on a constant number. People need constant condition for their day-to-day activities. Light level would remain constant, CO2, carbon dioxide, certain set point would remain constant. Even the temperature might change slightly. Okay, today I need 24 degrees, sometimes maybe 25, but not drastic change. But as Engineer Narang would highlighted, at the other end, when the chiller in, the load that the chiller is undertaking always will be changing. So that we have to have another system somewhere who is monitoring this load variation, and it should inform the chiller, okay, now you go to this set point. Now you go to this set point because the load has changed. Now we have got more people into the concerned area, or the outdoor temperature has changed, the climate condition, so that your current load is changing. So which means, as he clearly emphasized, we can't go ahead with the constant set point value always. So that's one thing. So that's why we need another system running on top of this, all the component, which would be monitoring these changes. So that's one reason why we need a building automation system, which will monitor the situation. And another reason, there may be a lot of reasons, but I will take a couple of highlights. Nowadays, we have a huge tendency, which I was highlighting also during my lectures, that we are trying to get renewable sources. For an example, artificial lighting together with natural lights. You might have a lot of windows, lot of openings, so that you will get natural lighting coming to the area. But the problem is natural lightings are not reliable. They are not constant. It's changing with the time, with climate condition. It's always changing. So that, however, our requirement, the light level that you have to maintain on the working area will remain as a constant value. So that you have to have some sort of a system again if you combine these two together, so that whatever the missing amount will be compensated by the artificial system, so that you will get the true energy saving out of that. Because energy saving doesn't mean you compensate the quality of your work. So whatever the required value, the required set point has to be maintained at the end, so that while maintaining these all, you get other system to run as per the user requirement. So that's one reason. So that's another reason that I have to highlight. And next one quick reason is, when you are buying these chillers and chill water pumps also, after the cooling load calculation, you are ending up with a number, so that you will go with, okay, chiller with this amount of tonnage, pumps this amount of RPM value or kilowatt value. They will have a range. Of course, your chiller can take the load up to some range, but again, there must be another system, as I emphasized before, to inform that, okay, you can't run on this particular constant value. It's changing now. The situation is changing. So that we need additional system running on top of those all, which will be monitoring and giving the relevant control signal to the component likewise. And other than that, with the timing also, these certain conditions are changing. Wear and tear. So such situation will affect to our performance at the end. So that's why we have to have a control system which will be monitoring this entire performance and finally adjusting them. So that's why we need a building automation system. I think modern building BMS is a must if you are looking for energy saving. I hope I answer your question.
I think Jagat, yes, good. That I think you connect these the other two expertise explanation into the good end for the first round. Thank you, Jagat, for your good and very solid and very informative introduction for the starting for the session. Audience, Zoom audience, I think so. The platform is open for you to raise your questions. So I know you have plenty of questions to raise from this panel members. So with respect to our course contents and what they have covered, so you are warmly welcome for bring your question and your experience and your challenges you face in the industry and your work experience. So the platform is open to you. So it's your session. And meanwhile, I focus to Engineer Kolita. Engineer Kolita, I think in your first interaction, you mentioned about the when you consider of the component, the chiller would be the main component. Yes, right. Chiller would be the main component. That's why the engineer Narangode mentioned about the dynamic the set point is needed, and Jagat explained how these are smoothing for the process. Okay, now as you mentioned, 70-60% it be the chiller. Now in Sri Lankan context for the design, actually we use for the water cooled chiller system and the air cooled chiller system. Actually, I would like to know on behalf of the audience. So how do you take that decision? Either we go with the water cooled system, either go with the air cooled system. So either how we set for the primary pumping system and the primary secondary like this. How on which point the engineer can take this decision?
Right. Thank you, Engineer Suru. I think your question is how we can select the system. I mean, whether we are going with the water cool system or air cool system.
All system. Yes, right. Yeah.
Is that your question? Yes. Okay. Fine. I mean, when we select the way, basically when we select the system, I mean, we have to pay our attention on certain facts. So, I mean, there are not only one or two, there are few reasons behind how we going to select the system. So actually, major one will be the efficiency. So, however, even though let's say now air cool chiller, when you take air cool chiller, so COP value now modern case it will be around 4 to 4.5, maximum 5, but that is a very high efficiency one considering the air cool. But when it comes to water cool, it's now centrifugal chillers, it touches almost 7.5 already. So that is energy concern. I mean, COP wise, that is there. However, even though COP wise, we cannot, everybody will think that we better go with water cooled chiller because the efficiency is high. But rely on that only, we cannot decide the system because I mean, some other facts also there. One of the main reason actually the water availability. Now, let's say I think if you have the experience in like Middle East countries, I mean, most of the systems that you see is air-cooled systems. That is basically the water scarcity is there because they cannot have water. I mean, like us, because we can have water at at low cost, but in UAE or Maldives even, they don't have that water resource. So then we need to think about how we can provide the water source to run with the water cooled chillers. So that is other fact to select which system we are going with. And space also, when you consider the space, now air cool system, if you don't need the condenser side circuit, I mean water circuit, you will be rejecting the heat through fans directly. Then if you take water cool system, then you need to have condenser pumps, condenser piping, then cooling towers. You need to consume a lot of space. So if you have space constraint, again that has to be again considered with system you are going with. Then not only that even if you have water, if the water quality is not so good, especially the normal chiller manufacturers are recommending to go with like TDS around let's say 1000 to 2000 around. So if you don't have the water resource with that water quality, or else if you have a water resource with bad quality, then we can't again go with, because you may have to have a kind of water treatment with a lot of maintenance and with maintaining cost and chemical cost, all those things will be there. So then another thing actually, if you take like cold climate, then again your air cool system will be working there nicely. However, if your chillers are working in high temperature areas, then again air cool will not be serving much. So kind of those specs we have to consider actually, your ambient condition, then space, then water quality, water availability, then another thing, capital expenditure for the water cool system will be higher than the air cool system. However, by looking at the capital expenditure only, we cannot work, because the other way, the efficiency or the COP value will be of the water cool system will be higher, and air cool system it will be lower. Then best thing, considering is all these water resources and water quality and all those things, you work out for the life cycle costing. So let's say around 15 years, you can work out with all these maintenance costs, chemical costs, and energy saving side also. Let's see, energy consumption. So with that, I think you can get a clear idea whether what system we are going on. But if you don't have water, straightforward, you can go with air cool at what cost. However, if you have water system, even if you don't have a kind of quality that expected from the chiller manufacturer, so best way I am telling, I mean, we can recommend to do a kind of life cycle costing, including maintenance, operational cost and everything, and go for a decision whether we are going with water cool or air cool. Yeah, thank you.
Very good, very informative the explanation, Kolita. Thank you very much. Audience, the forum is open for you. So if you have any question to ask from the panel members, I think so I can give the time. So when so because session is for you. So panel members are available to answer your questions. Still more than an hour is available for you to ask your question. I think so. I will go my next question to my next panel members. So Engineer Narangoda, I think there. So I would like to bring for the discussion. Narang now.
Yeah, please.
Yeah. Okay. Now in your first explanation, you mentioned that the dynamic set points are the unavailability of dynamic point and the running with the fixed speed and also manually operation. Even though we are doing the good installation, but operation wise is not optimized. So how do you think how effectiveness is a variable flow and the primary secondary circuit? Actually, I think you discuss about you and Polita discuss about during the session primary secondary system design and how these are effectiveness. How do you think how effective of the variable flow in the real Sri Lankan projects and what challenges for our engineers are facing to implement such system? And another point, how do you optimally select whether it is run as a primary variable or primary secondary like this? So how do you what sort of answer you can give for the audience?
Okay, so thank you for the valuable questions raised. Okay, there are two questions. I will take the first one first. Okay, so let's look at the variable flow operation against constant flow operation. Right? You really will understand even in the Jagat explained very clearly. Though the temperature, the final the space temperature is set to be 24 degree or 25 degree, whatever the set point. But the load, the building cooling demand, the heat load varies with the time. It's always continuously is varying with respect to the internal heat gain and external heat gain. So if someone thinking that constant flow would resolve the problem, is efficient, is not the way. It's not the real scenario there. So that is the problem itself giving the answer to go for a variable flow system with respect to the building heating or cooling demand or with the building heat load. But there are some constraints that we need to maintain during variable flow operations. We need to make sure the furthermost coil is getting the adequate flow and pressure drop across the coil. That has to be maintained. So, and the chiller from the other end, from the start point, the chiller should get the minimum flow which it is required. So those are the constraints that we need to make sure is always being maintained. from this end and from the other end. Minimum flow through the chiller and also the required flow to the last furthermost coil. So with that band, keeping those two parameters maintained, and you can flow the flow rate based on the with respect to the building heat or cooling demand or the heat load. So of course, I'm sure that you will get the advantage over the other through the pumping operation. The next question is which one is better? How to select whether primary
Primary.
constant, primary constant, secondary variable, or
Yes.
secondary primary variable systems, or primary constant, primary constant, secondary variable, or primary variable system. Yeah, that basically what my suggestion is to do a life cycle cost analysis. So when you do a design initially, the design is having two cost component. One is the initial capex, capital expenditure. The other one is the operational expenditure, the OPEX, which the design would carry after the installation is completed throughout the life of the building operation. So we have to do a life cycle costing with the system which I designed based on its capital cost and based on its efficiency respect to the building cooling profile, cooling load profile, and do a life cycle cost analysis and over at least 10 years and see which system would be the best for this particular building. Rather, we looking at only primary cost and secondary variable or primary variable system, but definitely the life cycle cost analysis would give you the answer finally, because it takes both your capex and opex into the equation and give a very balanced and precise and professional answer. So that's the answer, engineer sir, for your question. If anything, please raise.
Engineer,
your
your
sound-
mic is muted.
Engineer sir, your mic is muted, I think.
Sorry. Okay, thank you. Engineer Naran, so I will, your good explanation. So I will take up for the audience questions, which raised from then I will take up in the next round. So I'll directly go to the Kolita, because for taking the question from the audience, it's very simple question, Engineer Kolita now. Our participant asked about the selection of refrigerants. So very small answer. So such as R134A, R4110, the impact of the chiller plant. So can you give a short answer? Kolita?
Yes, engineer, the two refrigerant they're asking is R410 and R134.
R134A and R410.
Okay. Actually, R410 is normally we are having for the smaller capacities, and R134 is having for like 500 ton, like medium range chillers. And pressure wise, of course, 410 pressure is higher than the R134A. Then other than that, whenever when we select refrigerant, we have to care on like global warming potential and ozone depletion potential. Those two we have to consider. So other than that, the question is actually which one better is like that.
No, which one is more yes, which one is more better for the plant room? Yes, like that. So
Yeah,
I think
I mean,
that
if it
there's
is
no expression. It's there's no perfect answer like this, no.
Yeah, because no, actually, when it comes to chiller, like with a capacity like 300, 400 ton, definitely it will be coming with 134A. 410 actually not that high capacity chillers are having normally, and compared to 410 and 134A, 134A is better because global warming potential and these things are, I mean, less than compared to 410. So that is the answer.
Yes, thank you, Kolita. Moving forward to the Jagat. So, in order to continue, to keep a continuation to our the fruitful discussion, I think now, Engineer Narang bring that the how the selection is done for the variable and the fixed speeds and how this effectiveness, but they set up the strategies, but you took for the implementation part for the and of the commissioning part. So then is coming to the picture for the building automation system, the building management system, or either we can say the chiller management system. So in your experience, what is the biggest challenges when implementing this kind of system to the local project operation?
Yes, that's a very good question actually. Now, most of the time we strategize these possible chill water controlling strategies where we can get maximum efficiency improvement. But unfortunately, sometimes we don't get the sufficient help from the hardware. Certain components are not ready. Initially, somewhere some people strategize, okay, we'll do these kind of control strategies for the entire installation. But when you see the site, this particular design goes through number of cost cutting in short term. There are a lot of cost issues are coming in. So they will go with the bare minimum when it comes to the implementation. So because initially everybody thinks this, capital cost, how much that you are going to invest, and people very rarely think about the operational cost. Of course, some people do understand the importance of this factor, but what we have seen is initially they want to cut the cost so that they will come up with the bare minimum. However, in the document, they would expect massive controlling strategies. So many control strategies that we have discussed would be there in the document. But at the end, when the BMS engineer comes, who is trying to combine these two together, probably there won't be sufficient variable actuate at the other end. For an example, if you want to control the fan speed, so you can have star delta controlling straightforward, but it doesn't change the speed. So if you have gone through our lectures, as per the affinity law, you know how much would be the saving if you change the speed of the fan, if you change the speed of the pump. But if you do not have a particular actuator, such as VSD or variable frequency drivers, a similar device to control the RPM, of course, you can't get that result at the end. It's in cubic level, the result, the advantage that you can get in cubic. But unfortunately, the hardware is not supporting these things. This is the biggest issue we notice it. However, as BMS engineers, who are working in Sri Lanka, we have to understand these things. So our duty is to give the best rather than complaining and saying, okay, we can't do this, that, and. But it's our biggest contribution would be to give the best. When you do that as the BMS engineer, next thing is, okay, we see that now, as Engineer Narangoda said in his explanation, let's do the set point changes in various cases, dynamic set point changes. That has to happen. So that's the biggest contribution from the BMS. But at the same time, you must understand with the time, the system also changes. The dynamic component change. One good example is if it is an office. Now, initially, that particular area works as the office, but due to some reason, they might change into a storeroom. These things are happening always. Even our purpose of the building is dynamic. It's not the set point. Even the purpose of the building is also dynamic. So now when you do that, when you change the purpose of the building also to one purpose to another purpose, you must understand that system dynamics has also changed now. So that should be informed to the control system, which means you must tell now this load would change quickly or this load will change smoothly, something like. For an example, if it is office area, sharp 8 between 8 to 8:30, your load will be drastically going up as soon as the building start occupying. If it's a lecture hall, when the lecture starts, the load goes up. But if it's a ordinary store area, reception area, you don't see certain changes like that. So how do we inform this dynamics to the system? So that's where the loop tuning is coming in. So in Sri Lanka, I haven't seen biggest contribution or biggest involvement when it comes to loop tuning, because always when you control something, we are defining a closed loop. You measure the temperature and you check with the set point and then adjust the actuator. So this is a closed loop. So somehow closed loop should be adjusted as per the dynamics of the load. So these things are not happening right now in Sri Lankan BMS contest. Next thing is maintenance. You think at the very first day you set everything, you connect the cable, you connect the actuator, and you think that the BMS will look after everything. No, it isn't. It's a dynamic system. It needs care. You have to go there and continuously involve with this maintenance part. You have to check whether sensor is measuring the parameters correctly. That continuous interaction with the BMS has to be there. For an example, I have seen various buildings in Sri Lanka, World Trade Center building, Mireka building, where I am interacting with. Even those days I noticed Cinnamon Lakeside building. Those buildings, they don't know how to live without the BMS. That much of interaction is there, especially Engineer Narangoda. That's where he started his career. Mireka building, frequently that I'm interacting with. These places I have seen, this engineer, this staff, they don't know how to live, without the BMS. It's part of their life. Continuous interaction is there. So as long as you have that contribution and interaction only, you will get the output. So without that, of course, it doesn't work. It's just another investment only. So other than that, most of the buildings are not focusing on those things. So that's why we need those are the challenges that we are seeing. We don't involve with the BMS. We install it. We don't have sufficient hardware to give the best outcome. Then even though we install it, we don't do sufficient caring. So that's why we can't get the output as we expect. I hope I answer your question.
I think Jagat, I think same questions in your explanation. You have a bit broad explanation. The same question came from the audience. I think hope you may answer this one. This question is, in Sri Lanka, many buildings still operate without full BMS system. That particular the student asking how much efficiencies are actually losing due to this. Jagat, you are muted.
Yeah. This is again, based on the calculation. I think even Engineer Narangoda also emphasized this. For the moment, how much control strategies that you can introduce. For an example, in European countries, I have seen their document. Western countries and European countries, I have seen their documents. The extent of the control algorithm that they go. Whenever possible, they do that control strategy and save something. Even for the small amount of the chilled water or condensed air, chilled air, wherever they can save something. I have seen this in Singapore. I have seen some document from USA. Even a minor saving that they can take, they gain it. Why? Technology is not that expensive. When it comes to those countries, technology is not that expensive. Their energy cost is very high. But in our countries, both are very expensive. Energy cost is also very high and the technology is also very high. So it's very difficult for us to find out which one we should go ahead with. So it's the answer to that question. Actually, we have to think of the extent that we have to go. We can go. So based on that, I can give answer. But in Sri Lankan context, the extent of automation that we go when it comes to building automation is very limited based on our financial constraint. So again, I can't give a very straight answer on that case, but usually we say, as a thumb rule, we say at least 30% we can save by simply regulating the chill water temperature, the chill water valve or the chill water amount. By simply changing the chill water amount based on the set point value, you can save at least 30%. Having BMS, in thumb rule, we say that 30%, but believe me, it's more than that. if you can implement your control strategies to a greater extent. So that's the answer I can give there.
Right, Jagat, I think yes, the session is very, very interactive, and the questions are pulled in the chat box. I think I hope open the voice from the audience actually. So rather than putting the question to me, so I think we can filter those questions anyway. So anyway, so audience, I think the questions are regularly coming for the chat box. I think if somebody is willing to, okay, I think Chintaka Vikram Singh is switch on the mic. So Chintaka? No, okay. Any questions from the audience? So now the questions are coming. It's coming for the chat box. I really appreciate that. So I would like to open your voice actually. For the so then we can have the now productive discussion. Right. My next question to Engineer Narangoda. Narangoda, now actually, so I'll take some question from the audience as well. I think so. I can't limit for the one question right now. So time is very, very limited. So we'll cover whatever the things as much as possible. So my scheduled questions coming on now, Engineer Narang now. Actually now, so end of the day, so what our target is to energy. Energy is now whatever the system we use is energy. Now actually I know you have the good experience for the even discussion about the building energy index. So now because I think you have vast experience and you have some the international exposure as well as also now when we come to the green building concept also is a building energy index is a more key point. So now so what would be the in Sri Lankan our process in the sense for the design now optimization? So how important now I will be linking this question to next question for you, but just brief about this how we maintain the building energy index in terms of this plant room. Yes.
Yeah, engineers, thanks. Can you hear me?
Yes, Naran.
Okay, let's look at the questions in two ways. One is the efficiency, the other aspect is the effectiveness. So whatever the efficiency, whether efficiency is good or bad, so end of the day, end of the month, you pay to your utility authority for the energy consumed or for the energy consumptions that has happened in the building or in a particular system. So that mean basically what you pay is your operation on actual operation rather than efficiency. So that means what it says that if you can operate your plant very effectively with a very reduced energy, so that's what we should expect. Even with the efficiency slightly compromised, but if you can save the energy component at the end of the day, so that's we can buy hook or crook, so you get the things done. Mean that's the energy, reduced energy operation that we can expect. So in that sense, engineers, there are two basic parameters that we are looking at, energy efficiency or energy indices that we are looking at. One is the efficiency indices, the other one is the effectiveness indices. So you can waste energy. You can waste energy, being the best efficient person, having the best efficient system in your building. Right? I guess that you get my point. You can waste energy having the best efficient system in your building, right? Or another person can save energy even a less efficient system than that. That's why we are having two set of indices, one for the efficiency, the other one for the effectiveness. Effectiveness is basically talking about the specific energy consumption, or how much of energy is consumed per kilowatt hour, per square meter per month or per square meter per year, something like. Efficiency indices basically related to central chilled water systems are kilowatt per ton ratio. The engineer Kolit also explained very clearly. Nowadays we are looking at 0.6 kilowatt per ton plant efficiency overall, not only the chiller. chiller plus chill water pumps, condenser pumps, cooling tower all together to be at below 2.6 kilowatt per ton altogether. That is the water side. And plus air side, you have another benchmark. For the air side, you should operate below 0.25 kilowatt per ton. So that means the entire HVAC system, including water and air both, high side and low side both, must operate below 0.85 kilowatt per ton. Similarly, you can check at the end of the month whether your efficiency has given you the expected saving with double checking with the your effectiveness indices, which are we call air conditioning system efficiency indices. That is how much of energy is consumed for the air conditioning system per square meter per month or per year kind of indices. Singapore has developed few indices for that, for the total building. They have developed for the commercial category, they have developed some indices. One good example they say for the commercial building, the total energy consumption below 165 kilowatt hour per square meter per year. That means the building is energy performance wise is very good. If it is below 150, it's like building is excellent in terms of energy performance. But out of that, that is for the total energy of the building. From there, you can derive your air conditioning component and the other component. The air conditioning component is roughly around 50% of the total energy of a building. So that means if 150 kilowatt hour per square meter per year, so for the air conditioning, it's better to be below 75 kilowatt hour per square meter per year. That is basically for the commercial category. For the hospital and other industrial will be different benchmarks there for that. But we have to look at not only the efficiency, we have to look at the effectiveness as well. So that's my point is we should do the right thing and not always doing the right thing, and we should do the things right as well. So look at the efficiency and effectiveness both. Thank you very much.
Yeah, Engineer Narang, yeah, thank you very much. And where you bring for that energy wise in a good manner. I think you may have the experience in Sri Lankan implementation as well. You did for your past project in Sri Lankan Colombo. So now I would like to go your very first interaction about your that dynamic set point. Now the one our audience is asking this question. It's give a simple answer. The question is like that, based on what factors we can use a dynamic set point method based on the past data and the other facts. Can you get a simple answer?
So of course it cannot be past data because we are talking about a real-time data and dynamic set points. No? So it cannot be based on past data. It should be definitely based on the real-time data of the building. And for example, if you take a couple of examples like the real-time outdoor temperature, the real-time chill water return temperature to the chiller, and real-time control valve positions of HUs would make your call or give the signals or a feedback signal to your BMS algorithms to prepare a control loop, to prepare algorithms to get a dynamic set point. Because set point is not based on anything, is based on the real-time temperature or a heating behavior within the building, right? And cooling requirements through the central air conditioning plant. One good example, if you observe, the BMS observes a chill water return temperature is coming down, that means your automatic set points, the chill water set points, will automatically be going up or being reset to a higher value. So that's mean it's responding to your outdoor temperature, chill water return temperature, and control valve positions. The set point should be automatically adjusted based on a BMS algorithm.
Right. Yes. Thank you, Narang. I think yes. I think one our participant has raised his hand. The Madhushani. Yeah, Mrs. Madhushani Varnasuriya. Yes, Madhushani is. I think you can raise your question.
Hello, thank you. My question is to Engineer Jagat. And I would like to contextualize this question to Sri Lanka and would like to know, with the rise of the IoT, that is Internet of Things, and also smart buildings, how ready is Sri Lanka to adopt data-driven optimization in chilled water systems? Thank you.
So Jagat is, I think, so especially highlighting you two questions. Okay, you can answer this one. Yeah.
Yes, that's related to IoT. That's a good question. Thank you very much, Madhushani. Now, when you are implementing a control system for buildings, CMS or BMS, if you check the cost component, you have a labor because we need labor, we need to buy the controller, we need to buy the software, we need to buy actuator, and we need to buy cable also. How would you think the cost component would be shared? Due to rising copper prices, now the copper prices are going up now. It's getting very scared now. Next thing, the labor cost. Unlike fixing a sensor or fixing a device, when it's come to cable labor, it's very remarkable when it's come to a scenario like this. Because you have to pull a cable from one location to another location. It's not a very fixed cost. Sometimes you might face a lot of difficulties when you face another wall or something. You have to reroute it. So these are very unexpected costs. And on the other hand, sometimes buildings, if it is getting scattered to a larger area, this cable pulling, you have to use a lot of cable going to a various location. So now I have seen this cable component getting very significant. It's a huge component in a overall cost portfolio. But if you are using IoT solutions, IoT mostly on wireless solution, as long as you have the particular coverage, Wi-Fi coverage or 3G, 4G, 5G coverage. Sri Lanka has a wonderful 3G coverage. Sri Lanka has a wonderful 5G, 4G coverage. We are getting into 5G also. Everywhere you can have the signal. Wi-Fi, it's a very common communication component that we have in buildings. Wi-Fi wireless communication, we can fully eliminate this additional cost occurring these days. So now, whenever you need to install a sensor, you simply install the sensor via the location, and the communication will happen wirelessly. So you can minimize all the cost component occurred due to copper prices, due to labor, and other accessories, such as you might need a conduit, you might need a GI conduit, you might need a PVC conduit. All the additional cost component could be reduced. There are a lot of reasons actually I can highlight, but this is very significant where this cable cost could be minimized. So that's what I'm saying. Sri Lanka, we have a wonderful 3G, 4G, 5G coverage. People are very much educated about Wi-Fi technologies. Everybody knows about Bluetooth technologies. So Sri Lanka is fully ready. It's ready now. So it's a matter of it's our duty, all the initiative bodies like maybe consultant and entrepreneurs or investors, it's high time for us to include these new components, their document, so that it will be when it's come to the industry, there are enough people, there are enough engineers who can provide the services with this modern technology. So I can give you a number of examples, but I will use this particular example, cable cost. If you go with IoT solution, that entire cost component could be reduced. So Sri Lanka is ready. So I'm inviting all the consultant and the respective bodies. Please use this modern IoT and smart technologies so that cost could be minimized to a drastic end. So thanks for the question. I hope I answered with one example. But if time permits, we can discuss a lot, to be honest.
I think Ms.
Thank you
Madhushani,
very much,
yeah,
engineer.
yes.
Yes,
Yeah.
it actually explained really well.
Yeah, thank you. I think Jagat, I think you brought that for the challenges for the consultant as well as the government regulatory as well. Yeah, thank you. So this good point to focus. I think I come to the engineer Kolita. Engineer Kolita now. So I think the set not for the single question. I'm asking some question coming from the audience as well. Before that, I just want to now. I think you bring your plant efficiency, and you bring the how the selection of which kind of selection you can do, either air cool or water cool like that. So you brought this now. In your experience, I think you the more than 20 years experience in this field. So what are the most common mistake made in Sri Lanka, done in Sri Lanka, for when doing the plant room design? So you can give this answer. So I will come up with now I will attach some question coming from the audience.
Okay, well, thank you, Engineer Suru. When we talk about the common mistake, actually there are many mistakes happen in the industry. However, starting from beginning of the design stage, so from there onwards mistakes are happening. So one of them actually when you orient a building from that stage, we are doing some mistakes. Actually, now let's say when we think of orientation of a building, we have to think where the east, where the west, and sometimes architects, without thinking all those, I mean, energy concerns, they orient the building, finally end up with a high energy consume building. So those starting point we normally we have, I mean, many projects we have seen this putting windows and glasses, a lot of glasses in east and west directions, and without thinking the operational cost or the energy consumption. However, from there onwards, again, when it comes to the chill water systems, again, selection of chillers. I mean, many places we have seen selection of chillers for the building load without thinking of the load patterns or the load profile. People tend to select the capacities and type of chillers. I mean, of course, I think Engineer Narangod also explained in his lectures, when we select a chiller capacity and when we see a configuration of a chiller plant, we have to consider all those things. I mean, like configuration time, actually we have to select how best we can break the total capacity into number of chillers, like with the to meet the base load, then the variable load. Likewise, we have to have a kind of attention when we select the chiller capacities as well as type of chillers. Now, if you, I mean, because we finally we have to design economical as well as with minimum energy consumption system to the client or to the building. So when it comes to that point of view, of course, if you select kind of let's say now everybody talking about the magnetic bearing chillers. Now but if I say each and every building, each and every case, magnetic bearing will not going to work. So depending on the load profile, depending on the load variation, you have to go with, you have to decide whether the magnetic bearing will work or not. So likewise, because magnetic bearing cost side is higher than the conventional screw chiller or centrifugal chiller, then investing for a magnetic bearing sometimes will not going to work energy wise. So that's why I'm telling, so some mistakes are happening when selecting the chiller type and the configuration. Not only that, actually, now designers actually do their design and this pump head calculation and all those things with the design drawing. So, but however, when it comes to the installation level, we have to have a shop drawing, proper shop drawing, and recalculate all those pump heads and things because sometimes designer do with a lot of assumptions. Of course, that will not be the case when it comes to the reality. So when with the correct shop drawing with all coordinated, then if you can do the pump head calculation at that stage, then before you order the pump, then you could have order the pump with the correct pump head. In that case, actually, otherwise, if you normally what happen at, I mean, we have a lot of experience when you try to commission the pumps. The pump heads are, if the pump head is higher than the required or the system head, then what will happen? We will close the valve and try to control the flow rate. So in that case, what we are doing actually, we are creating additional friction to the system and maintaining the flow rate. So we are wasting our energy because we and that kind of mistake we have seen in a lot of buildings, especially condenser water side, even chill water side. Pumps are ordering with higher heads, and after comes we see in the commissioning time, you have to control with artificially creating the pressure drop within the loop to get the design flow. So those are the common mistake actually what we see. Apart from that, pipe sizing also. Actually, when we select the pump head, we have to consider the furthest loop or the highest friction path to get the head. Out of those, I mean, apart from that, whatever the branch pipe, you can have even higher pressure loss because it won't affect to the critical path or the highest pressure loop. When let's say now near to the pump room area, you will be having higher pressure. So you can have little bit high pressure drop in that area. I mean, of course, you have to consider the erosion of the pipes and so on. Velocity you have to think of in that way also. But however, you no need to go with the like 30 millimeter AQ or whatever your pressure drop per meter. You no need to buy in that area because you are having more energy closer to the pump room area. So likewise, those kind of mistakes are there. However, with from design stage, from the conceptual design stage, if you address those things, you could easily gain your plant room efficiency with kind of controlling BMS or CM through a BMS or 3MS. You could do it nicely. So I mean, those are many mistakes are there, but majorly we see those things when we going to implement systems.
Yeah, Engineer Kolita, I think I'm not going to leave from there. I think you answered this question as well. Now, one question coming from the audience is relevant to your now discussion. Actually, the particular participant is asking the this one. What are the operation advantages and limitation of the magnetic bearing chillers compared with the conventional centrifugal chillers? Now, when we go for the higher capacity, so now in a marketing point of view, they mention the high value, high IPLV value, and also like this. So I think questions are coming from the audience. I think you can give a short answer for this one. It's very good.
Yeah, as I explained, I mean, all the cases, the magnetic bearing will not going to work, as I said earlier. So, however, now you have to analyze the load pattern. I mean, if you have a kind of varying load, I mean, if your system is running with very low load, then of course you can go with magnetic bearing. Since the IPLV values are very good in the low load case, I mean low load areas. So, but make sure if you are running magnetic bearing chiller with a full load or 80% or 90% load, that is not going to work because you have like VFD chillers, centrifugal chillers, as well as screw chillers having higher COP than magnetic bearing at full load. You check with the reputed manufacturers. So your investment will be, useless if that kind of scenario is there. I mean, of course, if your system is experiencing low loads, you can go. Otherwise, you can evaluate the load pattern, and you in that with that load pattern, if you really feel 70 to major part of your load are having less loads or the part load, then you can go with. Otherwise, it is not going to work.
Yeah, I think you have given the good answer. I think hope that participants can be satisfied. Some one candidate, the engineer Chintaka Vikram Singh has raised his hand. Engineer Chintaka, I think you can voice for this session.
Good evening, engineers group.
Yeah.
Good evening, everyone. Actually, I don't know whether this question had been answered earlier because I joined a few minutes late. When I joined in the industry around 2000, there were a lot of air-cooled chillers. But somewhere down the line, I could find new installation. Now, people go with water-cooled. Any particular reason for that one, engineers or anyone can?
Yeah, I think Engineer Chintaka, maybe you may not be heard. I think Engineer Kolita has answered this one. What is the factor we consider for the air cool and water cool? Now this question is quite different. Engineer Kolita, now I just like to talk to you now. He mentioned
Just one thing to add. Actually, around 5 years back, I visited one of the reputed gown manufacturer where they had where they have a plant in Mayangan, where the water is very bad. We can find a lot of scale everywhere. Instead of, I thought that they could have gone for a air cool, but lot of installations are in water cool. Sorry, I don't know whether this had been answered earlier,
yes.
but
Okay. I think Engineer Kolita will be ready for the answer here.
Yeah. Thank you, Chintaka, bringing this question. Actually, like Mayangan area, as you said, the TDS values are high. I mean, hardness are very high. So, in that case, if they have invest for a water cool system after having the life cycle cost evaluation, that is fine, okay. Because otherwise, with the water treatment and all those things, sometimes they may be losing with the life cycle cost analysis. However, if they have done the life cycle cost analysis and done the investment, that is fine. But otherwise, they have to do it and see whether it is worth. Then, as you said, down the line, now we don't see that much of air cool installation in Sri Lanka, because that is because actually the one thing is the water resources available in Sri Lanka in Anuradhapura, Mayangani, those area. Even though we have kind of water quality issues, still they can manage with some water treatments, and they still prefer to go with the water cool system because the energy saving and the operational cost, life cycle cost analysis, we can see still savings are there. So that is the reason we go for water cool system in Sri Lanka. But when you go to like Maldives or Middle East countries, you can see almost all the installation are air cool. Very less installations are there with water cool. And on the other hand, one of the reasons why Sri Lankan people, even with bad water qualities, go with water cool installation. Sri Lankan Water Board actually charge very less amount for a cubic meter of water. With that, you can again go with even city water. So that is why most of the Sri Lankan places we can see water cool chillers, even though the water quality is not so good in their own resources. But they can use the city water and run with the system that will be cheaper than running with air cool. Yeah.
I think Engineer
Thank you.
Kalita has answered Engineer Chintaka your questions.
Very quick one. Initial cost, what would be the difference between water and air in the same capacity?
The adding component will be the condenser pump and cooling tower and the piping network. So those will be around 15 to 20% increment from the initial cost. I mean, this can vary with the capacity, but however, 15 to 20 around we can say, because adding part, because that also depends, because if you have your plant room in the basement, and if you have your cooling tower on top of the roof, having a kind of 30-40 floors or something like, I mean, depend on that, the cost will be changing for the piping network. However, we can say around 15 to 20%.
Okay, thank you so much. What would be the efficiency? Like, one question, small answer, like efficiency, right?
Water cool, if you go with water cool, actually, it's if it is a water cool centrifugal chiller, you can go now in modern cases like more than 7 even at full load COP. But
Okay.
if you go with air cool, it lies around 4.5.
Yeah.
Yeah.
Thank you so much. Perfect answer. Thank you.
Yeah.
Thank you.
Hope the Engineer Chintaka answer is, I think you got the answer. Yeah, thank you, Engineer Kalita. So now we are coming for the last half an hour for the session. So very interactive session. Lot of questions are coming and on schedule, but time is the limiting factor. So I'd like to bring Engineer Narangoda for the screen. Engineer Narangoda now. Yes. Now I think now we. This is practical question I'm asking, the practical issues I'm asking from you. Now, we bring the system is good design, and you prepare the good strategies, and from the Jagathen and he is for the control strategies and implementation. So now, how do you think about in Sri Lankan maintenance wise? So I'm asking this question in this manner. Now, like this. So how important is the operator knowledge and training? Because even though if we as a consultant, contractor, developer, so we give the good system, but for my experience, so we may have some poor maintenance. So how importance of the operator knowledge for and training for this system, maintaining in a good manner, and what are the gaps you identified, because you are in the maintenance sector as well, for the especially for the building, for the in Sri Lankan remarkable one of a remarkable building. Yeah, Nara.
Yeah, thank you, Zuru. Very good question. Yeah. Okay, let's think about like this. I'll take some provision for the answer like this. Say you are getting a very efficient car. You are getting a very efficient car, but if you cannot drive it properly, if your driving is not good, if you are not a professional driver, you cannot entertain its benefit. I'm sure. Similarly, air conditioning systems also it is applicable. From the project, from consultants, contractors, testing commission engineers, you may have got the best efficient system with you, but the operator's knowledge, their skills, their experience are not adequate to operate the plant efficiently and effectively, as I said earlier, efficiently and effectively to enjoy its benefit, then it's a real crime. So that's why we look at always both sides to get a very efficient car, and also to develop good drivers, to train drivers to drive it properly. So, so in that sense, I think Sri Lanka, all the days we had some challenges since we had no enough large central plants to get enough operators in our country. But nowadays, I have seen a lot of plants are coming up. Central application systems are there in our buildings, and also our people coming from Middle East get enough training from other countries. They are having the background, they have the experience. Only the lacking point of them is to understand the efficiency and operate the plant based on the dynamic efficiency, based on this we call efficient base operation. Efficient based operation. It's not just operating a plant. It's not something like you shut down the plant properly, you start the plant properly, you maintain the plant properly. That is required, that's compulsory. Plus, you must learn, operators must learn how to do a efficient based operation. So that is kind of a additional skill that we need to give to our engineers, supervisors, and plant operators. That's why we are conducting these type of courses and having these kind of panel discussions to eliminate certain barriers and get them to that level of skills. Thank you.
Engineer Narang, I think connecting to your previous explanation about the building energy index, this question I'm asking for the factual one. So one our participant is asking. This is not related to your now explanation, but the previous explanation. Now that particular participant is asking the sustainable energy authority, sustainable energy authority define the commercial building benchmark at the building energy index as 136 kilowatt per hour per square meter per year. This is asking whether this is accurate.
Yeah, okay. As I said, even Singapore sources says commercial building to be energy efficient, your specific energy consumption, they call total building energy efficiency indices, TBEE, should be below 146, even though I mentioned 150. This should be below 146 kilowatt hour per square meter per year. That is we call TBE, total building energy efficiency. In locally we call that is specific energy consumption. So in such context, to have SCC below 136 should be possible. It should be possible, but maybe a bit of challenging. Even the Singapore sources, they say that is below 146 is excellent. Below 136 mean it is really excellent if you can achieve that, but maybe a bit challenging. But with all these, the technologies, techniques that we are discussing here, and which are applicable to building sector, would definitely drive you towards the kind of a energy efficiency benchmark level. But most important thing is engineers know that our people should record this and develop graphical representations. They monitor their energy efficiency, specific energy consumption every month, and continuously monitor that and see how to bring it lower and lower possible year by year to a value that we should expect below 140 kilowatt hour per square meter per year. There's maybe a bit of challenging, but it's possible. And we have seen buildings operating that level. But there we need to make sure two things here. One is operation hours per day, because if some particular building is having more than 10 hours operation for a day, definitely their kilowatt hour consumption may be higher. But plants may be very efficient and the operators may be very skilled operators operating that very well. All other systems may be very efficient, but if the number of hours are higher than greater than 10, they are getting a higher kilowatt hour consumption at the end of the month. So there are corrections for that. We call occupancy correction factor, operation hour correction factor, that finally you remodulate or you reproduce. You are reproducing the specific energy consumption to reflect 10 hours of operation per day. So that's the reproduced figure has to be compared with the benchmark. So
okay, thank you.
We cannot say it is inaccurate. It can be accurate.
Can be achievable.
It is achievable. Yes, very good.
Yeah. Okay. Thank you, Engineer Naran. I think together with you, I bring Engineer Kolita for one discussion for the one question coming from the audience. Engineer Kolita and Engineer the Naran, you both you open for the question now. So one is asking for the redundancy. How we keep a redundancy when we doing the plant room design. Now we know we keep the 100% backup. N+1 concept we are bringing, and the duty assist concept we are bringing. So what do you know? Because why do I bring both? You know, as Kolita designed initially, then this control strategy is developed by the from Narang. So how both can answer this question? I think Engineer Kolita, you can start.
Yeah. Okay. Thanks, Isuru. When it comes to redundancy, actually, first of all, you have to configure the chiller plant room correctly to meet the base load and the variable load, so on, with the load pattern and so on. Then, once you configure the chiller plant room, I mean, with the chiller configuration, then you can think of the redundancy, because what redundancy do actually increase the reliability. Of course, let's say now for a 600-ton total capacity plant room, if you have kind of 302 numbers, even if you have 300 extra chiller, additional chiller with 50% redundancy, will work, because then I mean, of course, what you need, sometimes you maybe need to have a kind of pump interchanging, cooling tower interchanging kind of things you can have and even increase the reliability. Right? Let's say now, I mean, if you have a dedicated kind of pumping and cooling tower, then the reliability will go down. But if you can interchange these cooling towers and pumping, even you have dedicated arrangement, you can increase the reliability with even 50% redundancy. But that matters, all matters with the capex, I mean, capital investment. If you are capable of having 100% redundancy, of course you can have, but considering, I mean, nowadays technologies and all those short time delivery and the technology available and so on, I mean, even going 50% redundancy, okay, it's going to work, because not like earlier, whatever the let's say the downtime we can reduce with short time delivery and even keeping some spares with us. I mean, all those are there. So then with the correct configuration, of course, you can have even less than that redundancy also. However, this thing has to be evaluated properly and get the decision. I think Engineer Naranguda can add more.
Yes, Engineer Narang, I think you can add for the
Thanks, thanks, Engineer Kolika. You explained, I think, the most important part. Yeah, we should have in +1 or redundancy equipment for two reasons. One is basically to make sure that uninterrupted service for the building. Second one is not just to keep them on standby or on rotation mode. You can take the standby equipment also into the operation. Right? It's not something like you have in like duty roster for the cooling tower, for the chiller, for the pump, but you can make sure you can have those equipment also into the system. They are running, but if one fails, still the other equipment can take the even full load of the building. One good example is cooling towers. If you say, for example, you're having 3 cooling towers on your roof of the building, you can keep one cooling tower standby, two can be operated, and the next day the other two and the other one be standby. So but without keeping one standby, you can operate even all 3 cooling towers with VFD with a reduced frequency, getting more benefits to the air conditioning system, getting more savings in the overall system, but all 3 also contributing and running throughout the day. If one item, one equipment fails, but still the other two can take the entire system load. So redundancy mean it's not really redundant. Redundancy is there in the system, but that is not standby. That is not standby. That is also due to redundancy. That's what we call redundancy by duty. So that's the thing that we need to look at in that aspects. Rather keep them just on standby, you just line or just in plant rooms or rooftop, you can get their contribution to the overall plant operation.
Yeah, I think both with a good answer. Yes, thank you, both Engineer Kolita and Engineer Narang. So, so we have very limited time. I'd like to bring Engineer Jagat for the discussion. Engineer Jagat, so now you are the one coming for the implementation side for the actually design and implement for the BMS and the CMS. And like now, in previous discussion, Engineer Narangoda highlighted the how importance of having the operator training. So how now in coming over the chiller management system or the just the BMS, so how reliable this one? Because now let's open this discussion now. Always say clients say now අපි සුදු අලියෙක් තමයි මේ ගෙන BMS එක කියලා කියනවා. So then how why this happen in Sri Lanka? So what is the real case? It is a failure of the equipment or the failure of the design or the failure of the maintenance. So why? Can you give a short answer because now we are running up the time. So we are come to the end of the session. Yeah.
Yes. Again, it's not only for BMS. You would have seen in almost all the technologies in the modern world, like electric car, maybe our day-to-day Wi-Fi configuration, your computer. 10 years, 20 years back, using computer was a very tedious job. You don't know when it would fail, and you needed immense amount of knowledge in order to even run a computer or to configure. But nowadays, you have seen things are getting very easy. Configuring your Wi-Fi system has become very easy nowadays. Why? Because everybody wants to bring the technology to the end user very easily. Because if you make anything very complex and very difficult, nobody buys it. So one strategy in modern world is to make things, especially the operation, simplified. So that is happening now. Even for when it comes to building automation system, also this configuration, controller programming, those whole things are becoming very simplified and it's very easy to do. So which means technology getting accessible and it is touchable. People can use it now. So that is one advantage. We shouldn't forget that. So the technology, it's very near to us now. It's not affordable. Operation is not affordable. Configuration is not unaffordable. Sorry, not unaffordable. They are very close to us. So with that, why are we failing? That could be your question, I think. The reason is when you have a vehicle with you, now the vehicle operation becomes very easy. You know, all the interfaces are there. You would have seen this modern mission that you are using for accessing the going to the moon. You would have seen they have a lot of interfaces. The operation has become very easy. But the thing is, even the EV cars, Tesla or some other cars, a lot of interfaces are there. Operation has become very easy. But the thing is, if you do not maintain it, the operation doesn't mean, the maintenance has made easier. So you have to maintain it. You have to pay the attention. You have to check the sensor operation. You have to check the actuator operation. That's a mandatory part. When you buy a vehicle, you will pay some attention on the vehicle. You will take to the relevant location and do the services and all. You will pay the attention on tire performance likewise. So operation and maintenance, two different things. They are close to each other, but two different things. Operation has made very easy with the modern advancement of the technology, but that doesn't mean at the rear end we can forget. You have to have a proper interaction with the other end because they are the device which measures the current scenario, and there we have the device which take the action. So you have to have this particular interaction properly, then only you can get the full advantage at the end. So if you forget one side, of course, you will not get the expected. So that's the easiest answer which I can give you. So you shouldn't think that once you install and set and press the run button, it will do the job forever. No. It doesn't happen. Any engineering system, not only for BMS even, any engineering system, close interaction is very much essential. So does the BMS.
Yeah, thank you. Thank you. Very nice answer and very eye-opening answer, Jagat, you gave. Yes, very good. So, okay. And now the audience, you have any questions? I think you can raise. I think all answers, I think I covered given by you in the chat box. So if something is
Engineers, like this one or two questions there in the chat box which we have not answered.
Yes, okay. Yeah, okay. We'll take up this one. Yes, wait, Jagat, Naran. Yes, it's one question. I think, yeah. last question now is asking like this now. What is the maximum system water side delta T when selecting the closed circuit cooling tower? With the water entering is 40 and with the delta T is 8. Achieving when ambient wet bulb is 24. Now it is kind of a totally design point asking Nara. I think hope Naran and Kolita can answer this one. So in simply way, so this asking the closed circuit that achieving the delta T when the cooling tower delta T is at 8 and the water entering is 40. So it is no first my question is, do we applicable for in Sri Lanka?
I also can take a provision for this question. Engineer Kolith, if you are taking first, or shall I take first?
Yeah, you can take. Shall I explain?
Yeah, Kolith, you can take
Yeah,
start.
yeah. Okay. Actually, closed type cooling tower in Sri Lanka, I mean, a lot of application we don't use, but however, like water cool package units, we are having kind of small heat exchangers. Better go with closed type cooling towers. For that, actually, this delta T 6 to 10, yes, possible. 6 to 10 possible. But however, the 42, like other way you are asking, the 8 delta T you can go with, yeah, you can go with. When the ambient temperature, wet bulb temperature 28, of course, 32 you can easily reach. Yeah. Because normally in the open type cooling tower, actually, the 2 to 4 will be the approach. But in this case, it will be a little higher than that because it is a closed type one.
Kolita, now I'm just disturbing you now. Just engaging with your discussion. The maintaining the wet bulb constant level is a challenge in Sri Lankan for the RH consideration.
Yes.
The 28 and 32 is a gap. But if something at the more moisture level, it reach something nearly for the dry bulb temperature, no? Yeah.
Yes, because when you have higher RH, I mean that mean that the wet bulb temperature is closer to the dry bulb temperature. So, however, in the Sri Lankan context, actually, like 32 when the dry bulb temperature become 32 or 33, like except the coastal area, you are getting like 70-75 RH. That mean that your wet bulb will range somewhere 28-29. Then closed type one, actually closed type cooling tower. If you are the hot side temperature is 40, then you can go with like 32, 33. Yes, like 8 or maximum like 33, 34 better, I think, if you can design in that way, because there can be certain days where you have kind of high humidity and even with high temperatures. So then not like, because if you have an open type one, of course, the approach will be more better approach you can have, like 2.5, even 2 also can have, but with the open type, with kind of bigger design. But since it's closed type, yeah, 40, if you can consider like 6, 7, that would be better.
So, Engineer, sir, let me to
Yes.
add a little bit there in terms of the maintenance and efficiency. So I do understand basically we approach for high delta T condensed water or chill water is to reduce the pumping head requirements, and also that means to reduce the flow rate and thereby to reduce the pump capacity and to reduce the capital cost involved with the piping system.
Right.
So we can enjoy the benefit definitely. And at the same time, if that is condensed water, we are looking at condensed water, especially for high delta T, then we should look at the operational risk and energy drawbacks. Operational risk and energy drawbacks involved with high delta T condensed water. So if I highlight those, because we have to look at the pros and cons both and to make the decision. So what are the energy drawbacks is the high return condensed water temperature will increase definitely the compressor work done, and compressor has to work harder little bit harder than the standard delta T. So chiller compressor work done and chiller power consumption will be increasing with this concept. The operational risk that you will have, definitely high pressure, high condensing temperature, high condenser water temperature will cause high condensing temperature in the chiller refrigerant, which would cause risk for a chiller surge and risk for chiller tripping. So those are the risk of operation that you will have, and also energy-wise, you will compromise certain amount of energy from the compressor extra work done. But definitely you will enjoy from the condenser pump energy, reduce energy, and from the capital cost of reducing the pipe sizes. So look at both pros and cons, risk and benefits, and see which one is, which way is better to adopt to your system and the bill. Thank you.
I think Nara, now another question coming. I think you have answered this question now, because in last now is some audience asking is like generally we use 1.25 factor as a cooling tower selection. Now is generally is mentioned like the factor, the thumb rule like that for sizing cooling tower and the condenser water pump piping. Is it recommended to reduce this factor based on the condensation flow rate and entering leaving temperature? As I think you have answered this question. It can be basically reduced, but no, that.
I think Engineer Koditha can answer this very precisely. He has already answered.
Yeah, actually, as thumb rule, you can go with 25% because this is the heat what the compressor add into the system. The compressor work done will add some heat to the refrigerant, so that has to be removed from the cooling tower. So that is why the chiller load, cooling load plus 25% we add into the cooling tower. But if you can work out it closely with the chiller manufacturer, then you can get this load also. But when you are doing the design, of course, you can go with 25%. Then that is what they are asking 1.25 chiller.
Whether they can go with the reduced factor to reduce the pipe sizing and flow rate, like keeping the entering leaving temperature is quite high.
You can, because the thing is actually you can reduce it, but at the end of the day, if you are not getting the required design temperature into the chiller, that means condenser water temperature to the chiller, then you will be ending up with again high energy consumption, because whenever you have a kind of higher flow rate to the condenser side, you will get more cool water, right? Of course, you have to size the cooling tower also accordingly. Nowadays, actually, you can see, with low entering temperature, the condenser will yield more energy, more COP to the refrigerant circuit. So when you have high temperature entering into the condenser water side, refrigerant, as Engineer Arangoda said, refrigerant discharge temperature and pressure will go up, and it will be more work will add to the compressor. With that, your COP level will go down. So those things you have to be careful when you are changing these factors, and even you can have kind of more delta T and reduce the flow rate, but if it is really not working with the cooling tower, then it will affect to the COP of the chiller and finally the plant room efficiency.
Basically, Koditha, now you mentioned the factor is not the thing, so we can decide, we can do whatever the things, but anyway to maintain our system performance. Yeah. Okay. Now we have come to the end of the session, but before that, I think I would like to bring all three panelists for the common discussion for this very short time. So Engineer Narangoda, Engineer Koditha, and Engineer Jagat. So this is open. This question to open to you. You can all can answer in your point, your experience and your thinking like this. So now we have this. We are discussing throughout this almost 2 months about the plant design and efficiency. So in your experience and in your exposure for this field, so what would be the future? Where we are in our plant room, like now in Kolita can discuss about the which kind of efficiency wise high level equipment can be placed, and in Narangoda you can bring for the how much of more technical advancement can be bring, and what are the technologies you can bring for the control strategies, and Jagat can bring for the next level IoT level. He has discussed in this session also, but what are our next thinking level? What would be we are in next 10 years time when we're doing the plant room? Can we start from Engineer Narangoda? Yeah.
Okay, Engineer Suru.
So
my
but-
first my first ambition, if I can provide AC without energy in the next 10 years, that's my ambition. That so what in other words it says to provide, because we need to maintain thermal comfort. Because that requirements are it's not like old days. Now it is really important to maintain thermal comfort due to many reasons. One is the global warming. We are really becoming really uncomfortable in the environment than 20, 30 years before. So we need to maintain thermal comfort to maintain our productivity in all aspects. So, and the other end, the challenge is the energy. Energy cost increases. Energy going to be is becoming a limited resource in the world, and your demand high and your supply becomes lower. So that's the challenge that we are analyzing for the next 10 years, 20 years, 30 years, 50 years ahead. So demand going up, but your supply becoming challenging. So in such case, then what engineers can do, my opinion, in that context, what engineers can do is to design proper systems, efficient systems, and coupled efficient control strategies to run it efficiently and operate it efficiently. So that's what engineers can do at the moment. But engineers involved with technology can look at more wider, broader technologies and newer inventions to have another dimensions of these aspects. But as engineers in this end can do maximum to design best efficient systems and also to operate or to have couple efficient strategies into the system and operate efficiently. So that's what we can do. So that's why we all are here. That's why we all are learning. That's why these kind of CPDs are being conducted. I guess our team has got something from this and definitely would involve with active practical engagement in their day-to-day life and provide and do the best service for the society and the country. So thank you. Over to the
Yeah,
other
thank you, Engineer Narang, and Engineer Jagat. I will keep you for the ending note for this special panelist discussion. I will bring Engineer Kolita. So, what do you think now? I think I know some interruption, Now we are discussing about the open discussion from among you. What do you think about our next level in our 10 years, where we are in the plant room and energy optimization design? What do you think? So, what is your message to our participant and audience?
Actually, sorry, my line got interrupted.
Yeah, I know.
Yeah. Then when I come to your question, Engineer Suru, actually we are far behind with the world because now most of the countries they are running behind these benchmarks and daily updating these benchmarks, and each and every building they are monitoring their running running status and comparing with the benchmark, and day by day they are improving their efficiencies of the systems, and there is no end, because we thought when we engage in this industry in 2000 around, so we thought the chiller efficiency will be ending up with somewhere like COP 5 or somewhere, but it has now gone to 7.5. I mean, I don't think that it is the end. So it will be day by day, they will do some R&D work and develop. I mean, even chillers, pumping, and all those things. Of course, actually, nowadays, we have these technologies available available to our fingertips. So what we need as a professionals in the industry, every day keep your knowledge updated and go for the new things and go for new products and search for new technologies. And especially even though we install very sophisticated whatever AI control or whatever it is, you have to maintain it and monitor and see whether your expectations are met or not. So what our maintenance in our country, what our maintenance teams are lacking, they hand over everything to the BMS and they are staying in the room and see, just observe, not think and controlling, and not checking with the live data or whatever the current data and whether we can improve or not, and they are not comparing the benchmark or the improvements. So in 10 years time, at least if we can develop these things into that level where the other countries are doing these things, like especially like Singapore, they are kind of promoting these kind of zero energy building and this energy benchmark and whatever green buildings concepts and all those things. So we also have to go to there. So otherwise, with the energy crisis and all those things, we will not be surviving in the world. So I think it's good time for us to think, rethink, and move forward with that intention.
I think nothing else from Jagat. I think you can have a good ending note for this discussion. So with that, my concern, what would be our next level?
In 10 years' time, I think that's the
Yeah.
number you highlighted. So we will be older. That's the first thing which came to my mind, that 10 years will be added. I'll give a very quick example what is to happen in a remaining period in the future. Recently, in one of my buildings, this all the solar panel, everything was at the roof level, the inverters and everything. However, these inverters to be connected to the building automation system, but there were no any cables and that area. So this was challenging. If I happened to pull another cable while the building was almost at the ending phase, it could have been a huge challenge. So when I was investigating the other option, I noticed that there was a wonderful Wi-Fi coverage up to the inverters and that area. So then I said, okay, you emphasize the Wi-Fi coverage little stronger. That having a Wi-Fi coverage was just merely changing the orientation, and then we could get entire data, the load and current and everything to the connected to the BMS. It's what we did was simply changing the orientation of one Wi-Fi antenna, rather than if I happen to pull another cable and do the program and everything, that could have cost close to, I think, 500,000 Sri Lankan rupees with GI conduit and everything. So simply I changed the orientation of Wi-Fi antenna and got the requested information, almost no cost. So I think that example itself gives you the future. So things are becoming very easy, things are becoming very cheaper. So if you utilize the particular technology is almost there. So it's a matter of using the technology at the correct place and the correct time. I think we have the resources, we have the people, we have the expert in our country. So with their combination, I also have seen almost all the consultants in the country right now are promoting BMS. That it's a challenging thing. I know it's a challenging thing with the restricted budget and certain other constraints. Promoting a BMS has become a huge challenge, but still they emphasize it. It is needed due to current other challenges we face, like energy crisis and environmental issues, so on and so forth. So we have to admire them. We should invite them to promote it further and further. And we do have some constraint. I heard that engineer Kolit also highlighting this AI part. There is another use of AI. I told you we have some restriction when it comes to hardware usage. We have limited controllability when it comes to hardware usage. You can utilize AI tool to promote strategies, suggest us the strategies with this limitation. That's another approach. We are doing that. Sometimes, the project, we might have some constraint and limitation in terms of hardware. You can utilize AI tool to give us some input, use this strategy for this particular building based on. So such implementation is very much possible. So I think the future is very bright for me when it's come to control side. We are looking forward, and I'm inviting, especially through this program also, a lot of students are being exposed to this new wording and new ventures that are happening out there. So I'm inviting you all to be with the this development. And I'm thanking each and every individual who contributed to ask the question and kept us alive. Otherwise, these kind of sessions are very boring. We have taken somewhat longer time, but many people kept in touch with us. So thank you very much. We are looking forward to deal with you even in the future. And thank you very much for the organizing committee for inviting us for this wonderful venture. Thank you.
Thank you, Jagat. Thank you, Naram. Thank you, Kolita, for wonderful session. Actually, so from the initial stage, for the develop this course module and for the panel discussion, you have done the real job with our teams. That's credits go to all of you because your expertise and everything is very, very passionate and very, very truthful. And now its result has delivered to our industry, not even for our limited student. Now it is being broadcasted all over the world to the YouTube and Facebook. So now you are now fully international batch now channel now engaging now. So very, very happy to now very, very fruitful discussion. So now we have come to the end of this session formally for the week, almost 2 hours completed. So with the formal vote of thanks, I would like to invite Ms. Senali Hulugalla, who is the marketing executive of the Building Service Industrial Campus. So in the vote of thanks, Ms. Senali, so it is over to you.
Yes, thank you, Mr. Lakmali Suru. Good evening, everyone. I'm Junior Architect Senali Hulugalla, Marketing Executive of BSRC Campus. So as we come to the end of this insightful program on central chill water plant design and efficiently optimization, it is my privilege to deliver the vote of thanks. So first and foremost, I would like to express our sincere gratitude to our distinguished panelists, Engineer Prasanna Narangoda, Engineer Kolita Vanasiri, Engineer Jagat Vikramasekara, for sharing their valuable knowledge, practical experiences, and professional insights. Your contribution have truly enriched this program and provided immense value to participants. I would also like to extend our heartfelt appreciation to our moderator, Engineer Lakmal Isuru, for steering today's discussion very smoothly and professionally. A very special thank you goes to our audience both here and those who join us via Zoom, Facebook and YouTube. Your active participation, thoughtful question and engagement added real depth to this discussion. As it is often said, a good question is never answered, it is explored. And I think today's interaction truly reflected that spirit. We would also like to sincerely appreciate all the students who have been with us from the very beginning of this course. With this, we officially come to the end of this program and we will be arranged to deliver your certificates in due to course and further details will be communicated to you soon. Once again, thank you all for your time, participation and support. Wishing you all the very best in your professional journey. Thank you very much and good night.
Yes, thank you.
Good night.
Good night.
Good
Good
night.
night.
Thank you. Thank you.